Good morning. I'm Nirmal Ghimire from Department of Physics and Astronomy and Quantum Science and Engineering Center at George Mason University. And today I'm going to talk about quantum materials. I'll try to give an overview of what the quantum materials are, and then the kind of effort that on the study of quantum materials here at George Mason University, and in particular the Quantum Science and Engineering Center. And I'll kind of briefly so some of the results that we are getting from our research. It's from my group, just as an example of the study of quantum materials. I'll start with a brief background and then an introduction about the quantum materials, and I'll give you an example of a quantum mechanical phenomena, and we'll provide some materials examples related to that phenomena, and then I'll summarize the talk. Let me start with this picture, and for those who are from GMU, this picture is not unfamiliar, right? We have these little robots that are delivering foods. Now you can just order with the app, and then the robot comes with the delivery. And the reason is why I'm starting here with this is a question, right? What I'm trying to show you is that I'm trying to allure you about our future. What kind of future that we are thinking about? What is our future going to look like? Maybe a decade or 2 decades from now. All these artificial intelligence and things are coming along, and to kind of match with that and to get this technology forward, what we need is new materials. And before going into the future, let me go into the past and kind of try to correlate our human civilization with the materials. So it has been pretty remarkable that the march of a civilization has been marked by various signature materials. We talk about the Stone Age, Bronze Age, Iron Age, and Silicon Age. We are currently in the Silicon Age. So, we can think of how impactful it would have been when people discovered bronze, which we now take as a granted, right? The utensils and the hunting tools that the people could make had changed significantly the lives from, when they were constrained to use the stones. And then when the Iron Age came, all the industrialization happened. And with the silicon, I do not need to exaggerate the thing. I probably couldn't have been able to do even this presentation without the boon of the silicon technology. So if we now want to move past the silicon technology, which we know that it's already started hitting the limit, is we need some sort of new materials, right? And what kind of material that be is an interesting question, and that is what mostly the effort in the study of the materials is. So before defining our quantum materials, what kind of phenomena we want in the materials, I would like to show you a video, and it's about 3 minutes video, and then I'll kind of correlate this with the materials.
Attracted by the heat of the city, 5 million starlings stream into Rome. Before they roost, their maneuvers create nature's greatest aerial display. Their iridescent plumage is lit up by the setting sun. But this spectacular performance isn't for fun. The peregrine falcon is looking for his evening meal, and he's hunting the world's best formation flying team. Their mesmeric waves confuse the peregrine. He can't lock onto a single target. achieve such synchrony, each star shadows 7 of his nearest neighbors. They react 10 times faster than any human pilot. To stand a chance, the peregrine must up his game.
Stop this video. Okay, sorry about that. Okay, so I just showed this. I was talking about quantum materials, and all of a sudden started showing the video about the birds, right? But we saw something interesting there. So what was happening is that the birds were kind of flying on their own, and then what happened is that a hunter bird came, and in order to protect themselves from that predator, these birds kind of started shielding themselves, right? It was mentioned in the video that one of the birds was able to shield 7 other birds, and then and they started moving faster. Because of that, a new formation, kind of an amazing formation, appeared on those birds, right? So we can correlate that to materials. For example, the simplest materials that we can think of is the hydrogen atom. It has only 1 electron and 1 proton, right? And we know all the description of the hydrogen atom. We can take this as a single bird. Now, materials is pretty complex. We have many elements in a material. Each element can have many electrons. So how to deal with these electrons and how to know the properties of this material system, right? It's complicated. But if these birds are kind of flying in parallel, which is if these electrons are not interacting with each other, if these are simple, then these properties can still be predicted. But what happens when a hunter bird situation comes, right? That is where the quantum mechanical phenomena plays a role. And then, can we get some sort of this type of features and emergent behavior in materials that can be potentially useful? We have studied almost all the materials, their physical properties, right? Now we need some emergent behaviors to be used in future technology. So that is kind of an interesting aspect, and the materials. Now, in which this extraordinary effect comes because of the quantum mechanical phenomena are the quantum materials. This is one of the ways these quantum materials are described, and there can be many other definitions for the quantum materials. So now the question is, why do we need quantum materials, right? And the thing is, over the course, if we look at over the course of the time, these different physics have evolved. Now we have several different these emergent behaviors in the material that in different aspects people are studying in condensed matter communities. Either this anomalous Hall effect or spin Hall effect, multiferrics, and a lot of the different things. I'm not going to even name them all. What I will kind of try to point towards is that all these different emergent phenomena can give rise to potentially useful applications. For example, we can think about these topological electronics. What the topological electronics does is that it reduces the heat dissipation, right? Some dissipation, less current flow in the material. We use our laptops, phones, and they get heated. So if we can get a dissipation less for electronics, then that can help not only to save the battery life, increase the battery life, but enhance the performance of those equipments as well. And the next is the quantum computing. Our CPUs has hit the limit, right? It's been several years that the performance of the CPU has not increased. We are making supercomputers, but that is because we are stacking the CPUs. So if we want to now go past that, we need some new materials platform. Room temperature superconductivity or above room temperature superconductivity can be another game changer, right? That superconductors can be used to generate very large magnetic field, then we can think about these levitating trends and so on. This motortronics is using physics called morphysics, where the metal insulator transition occurs, and that kind of phenomena can be used in designing or making some RAMs, which is this is REM is a resistance RAM. So there are different these phenomena that can be these are the things that we can think of from coming from these emergent phenomena, and where to find materials that are more geared towards can we get these materials for applications to the future technology, and that is why the quantum materials there is the interest in quantum materials. Now, what we're doing here in Quantum Science and Engineering Center is that this is a group of people across 2 different schools covering 3 different departments. We also have some affiliate members from National Institute of Standards and Technology, NIST. And we are kind of working on various different aspects of the quantum materials, from first principle calculations to quantum field theory, theoretical design of quantum materials, and this NQR study of these quantum materials growth characterization, low-dimensional materials, 2D magnetism, flexible optoelectronics or photo electrochemistry, electron interferometry and low-dimensional materials, then atomic and molecular spectroscopy. But I cannot cover all these things. What I will do in this talk is give you kind of a flavor of what my research is about in these quantum materials. And my research is about the material synthesis and magnetic transport study. So what we do in my lab is we grow materials in single crystalline form. So here are some examples of to get the laser pointer. All right. So here are the pictures of some of the crystals grown in my lab. Then we characterize these materials that we grew in my lab by various techniques, and we measure their physical properties to kind of study the quantum mechanical properties. And one of those quantum mechanical property that we are studying is topological Hall effect in material. And now I'll kind of briefly show you why this topological Hall effect is a quantum mechanical phenomena and how we are studying that very briefly. So in order to understand the topological Hall effect, first we want to understand what is a Hall effect, right? Hall effect is not necessarily a quantum mechanical effect. It can happen even with classical charged particles moving in a magnetic field, right? If we have a current, which is the flow of charged particles and subjected to a magnetic field perpendicular to it, then the charge gets pushed by the Lorentz force, and then there is a potential difference developed across the material. Then we can measure this potential difference in terms of resistivity. So this resistivity is called the Hall resistivity, and the Hall resistivity is usually proportional to the magnetic field. And this is a fundamental property of all metals or all conductors, right? And it was Hall who, this was discovered in 1879, a long time ago. And Hall himself also discovered that when these materials are magnetic, then, the Hall effect can even appear without magnetic field also. And that's called anomalous Hall effect. So for example, there is a ferromagnet. This ferromagnet has certain magnetization, and the anomalous Hall resistance is proportional to the magnetization in this case. And this is the magnetic moment as a function of magnetic field. And because of the hysteresis, there is this remnant magnetization. And that corresponds to the anomalous Hall effect, the Hall effect appearing in zero magnetic field also. There are various different types of magnetic structures, the conventional structures. This is the ferromagnet that I showed you, where there is a net magnetic moment that we can measure. And there's antiferromagnet, where spins are pointing in opposite directions, and the net magnetic magnetization is cancelled in this material. Ferrimagnet, where spins in one direction is larger than the spins pointing in the other direction, so we have a net magnetic moment. So it's kind of something between the ferromagnet and antiferromagnet. When these spins are disordered, mostly by the temperature in most cases, then this is a paramagnetic state, right? But these are the conventional magnets. There are various interesting magnetic structures that have been realized, and those some examples are here. In this case, these spins are pointing in different planes, so these are non-coplanar ferromagnets. In this case, the spins are in the same plane, and they are antiferromagnet. That means they are canceling the effect of each other, but they are not in the same line. So as I showed you earlier, so these are non-collinear antiferromagnets, and this is a very complex type of magnetic texture, a hurricane-like texture. This is called skyrmion, and these textures allows a quantum mechanical phenomena to appear when the electrons move through these textures, and then it picks up a phase that can give rise to this topological Hall effect. I'll show you briefly about this thing. So if we want to understand that why these materials show these, what kind of quantum mechanical phenomena these materials. So I'll kind of briefly show you this phenomena where there is a pendulum at the North Pole, and I'm taking this pendulum, letting it to swing along the direction of the Portland freely without jerking. I move this pendulum towards the equator, and then when I come to equator and move along the equator and go back to the same position, then what is expected is that the pendulum will swing in a different direction. Okay, it's hard to do, but we can kind of understand this by taking some vectors and taking even a globe, right? So I take a vector here. So the vector is these two directions, and then I move this vector without twisting and turning smoothly, and then get back to the same position. But what happens is that it makes angle. These vectors make certain angle to their initial position, right? So this angle is purely geometrical in nature. It comes entirely from the curved surface of this globe, right? And this is a geometrical angle. So I will kind of show you a video here that kind of shows the same effect. So what I'm doing is I'm just making those arrows as a vector. And I take a globe and I will kind of move it through the globe. I started from that original position, went to equator, come back to the original position, and without twisting and turning locally. But globally, what it does is that we can see now when it comes back to the original position, these vectors are not pointing in the same direction. So that means such a process is called non-holonomic process, and the angle is obtained just by moving in a curved surface. This doesn't happen if I move it on a plane surface, just like on a tabletop, right? And similar thing can happen with the electrons when they move through these kind of spin textures. And that's why I kind of named these as quantum magnets, because there is some quantum mechanical phenomena that can be generated with these magnets. So this geometrical phase, sorry to put this here. The only reason I wanted to show this equation here is to show you that this is basically the quantum mechanical phenomena, that angle that electron acquires by moving through these spin textures is called the Berry space, and then Berry space is equivalent to the flux of a magnetic field. So whenever an electron moves through these type of textures, what happens is that the electron pick up a phase, and when the phase is picked up, the electrons feels a fictitious force inside, fictitious magnetic field inside the material. Now, electron is a charged particle, there is a magnetic field, it experiences a force, then it gives rise to the Hall effect, right? So this Hall effect is topological Hall effect, and entirely different from the Hall effect that the Hall measured in 1879. Right. So I will briefly show you an example of a couple of materials where we observe this kind of topological Hall effect. If this happens in zero magnetic field, we still call it anomalous Hall effect because it appears in zero magnetic field. It can happen in magnetic field as well. So this is a compound that has a collinear antiferromagnetic state, and in collinear antiferromagnetic state, an anomalous Hall effect is not expected. But when we measure the anomalous Hall effect, this is the magnetization. It has a very, very small magnetization. If I have to compare it with a known ferromagnet, which is an iron, this value is almost 1,000 times smaller than that what you get in iron. But when we measure this anomalous Hall effect, the size of the anomalous Hall effect is as large as you get in iron. So this is 1,000 times amplified anomalous Hall effect in this material. And the question is now, where is it coming from, right? We have given some, we have proposed some mechanism for it, but there are other mechanisms also coming up. So I'd say that this is still not yet clear why this anomalous Hall effect is observed in this material. And then there is another Hall effect that we recently observed in another compound, this yttrium manganese 10-6, where there is the topological Hall effect appears at only certain temperature range. So this is temperature, and here is magnetic field. So only within a certain range of the magnetic field and temperature. So at lower temperatures, there is no such Hall effect. At higher temperatures, no such Hall effect. Higher magnetic field, no such Hall effect, and lower magnetic field, nothing. It just happens within a certain range of temperature and magnetic field. Then we mapped out what kind of magnetic structures can there be in this material, and we mapped out the phase diagram. These are the various phase diagrams, and we realized that these topological Hall effect occurs in this particular state, which is called this TCS, or what we call transverse conical spiral. And this is basically particularly this structure. We now know what structure of the spins are there in each of these phases. And what we then this particular phase is not able to generate the topological Hall effect in itself. And while studying this, we realized that a new mechanism, the temperature stabilized mechanism, gives rise to this kind of topological Hall effect. Here, this red one is the measured topological Hall effect, and the blue one is theoretically calculated topological Hall effect based on that model. So we believe that we have this new mechanism for a topological Hall effect. So this is the kind of thing that we are doing in the study of quantum materials. So in summary, I kind of try to give you an introduction of what quantum materials are. These are these materials that show emergent behavior due to extraordinary effect of quantum mechanics. There can be many various different forms of quantum materials. And then these quantum materials may shape our future technology. And in fact, if we have to change our technology to the next stage, it has to through some materials. And then these anomalous and topological Hall effect are associated with a quantum mechanical geometric phase, and it's kind of an example of the quantum mechanical phenomena that I was discussing, and I basically showed you how we do this kind of research in particular materials, and I showed the example of the two materials. And with this, I would like to thank you, and I would like to take questions that you have.
Thank you, Nirmal. For questions, please feel free to unmute yourself and ask, or you can put a question in chat.
But if there is a question in chat, thank you. Could you please read, because I don't have access now to the chat because of the screen sharing.
Okay. Actually, there's no question in chat now, but I do have two pre-collected questions. One is, I guess, from an undergraduate student. He or she is asking how can he start working with any professors on this area? How do they, who they need to talk to, and how do they start? Oh, so the starting point is that you go to the our quantum centers, the Quantum Science Engineering Center's website, and it's listed who is working on what kind of quantum materials aspect. It's listed there. You will find the information, emails, and then the kind of work that its group is doing, and you can send email to people, and the professors, I believe, would be happy to talk to you about their research, and I think that's the starting point. That's the point to start. Thank you. And another question is about two-dimensional materials. I think the student is interested in working on the two-dimensional materials, probably graphene or something related, and I want to hear a little bit more about this. Can you briefly introduce that a little bit?
the two-dimensional materials. Two-dimensional material. Graphene is a two-dimensional materials, and we have two professors or two or three professors in quantum science and engineering center who are working along this line. And one is Faresta Ghimire, and another is Professor Patrick Bora, and Professor Pilgyu Kang is also kind of working on these 2D materials. Basically, graphene is an example of 2D materials, and graphene has very interesting properties, like it has these topological band features like Dirac fermions in that material. And it also is kind of prone to susceptible, very susceptible to some the gap opens very easily with external perturbations, and then this has led to two entirely new different fields. One is the study of these two-dimensional semiconductors, and the another field is again the topological materials, where we have these Dirac cones, wild semi-metals, and all these things. This is a kind of a general overview of these two-dimensional materials currently people are studying. And then if you have any specific questions on that, might worth checking with Professor Vora or Professor Gary.